Ladies and gentlemen, it's a pleasure for me to announce on behalf of the VDMA Machine Vision Board the winner of our startup competition, startup award. It's Visiotics, represented by David. David, first of all, the most important thing, another bottle of champagne. Enjoy it. And the trade show of Stuttgart will sponsor the next booth for the next year, or for the next Vision show in 2026, as a little award and a little bit of, let's say, money worth contribution. Thank you very much. See you next time on the Vision Show, right? Thank you.
Perfect. So, welcome back for the Industrial Vision Days. Next session is going to start. And it's another hot topic. It's beyond the visible, hyperspectral, and so on. So, my first speaker is already with me. Perfect. It's James from the company Living Optics Limited. And he is going to talk about raising a glass to snapshot spectral imaging in viticulture and beyond. Looking forward to it.
Perfect. Hello. I'd like to start with a statement that hopefully everybody in the audience is biased to agree with, which is computer vision is the future. So I'd like to explore a little bit what that future could look like. For us at Living Optics, that means computer vision that is everywhere and used for everything, able to solve existing automation problems in almost any setting, and enabling more informed decision-making across all aspects of our lives. So how do we go about making this future a reality? We do this by addressing the biggest limitations of computer vision today. In the next few slides, I hope to show you how Living Optics camera gets us one step closer to that future. So for any item to be used everywhere and used for everything, it has to be really, really useful. In computer vision, that is the automation of tasks. This is currently enabled by asking machines to extract information, visual information, from images that we capture about the world. Too many of these interpretations can fall over by everyday use cases. If we take the example of the image at the top of the screen, we see an apple and a sports ball. As soon as a hand comes in to grab it, the classifier has classed the apple as a sports ball incorrectly. It's confused by the context. Similarly, we have an example with ChatGPT trying to describe this image shown here. It thinks it's a crowd of people at a concert with large amounts of lights. It's actually combine harvesters going through a cotton field. It falls over. How do we address these confusers? Well, normally we throw vast data sets at them, but this is extremely costly and it takes a lot of time. So how can we perform better at these interpretations? Well, one way is to extract more information from what we're already looking at. Enter hyperspectral imaging. So conventional cameras to date, like the ones in your phone, use 3 color buckets, red, green, blue. And these are really good for taking pictures of holidays, your family, your pets. But for training machines, it's a bit of a legacy technology. We're limiting the information available to machines from the outset. Hyperspectral imaging takes the light and cuts it into many more color buckets. And this provides a much more detailed and rich description of objects around the world. This is far beyond what RGB can ever offer, and we call this description a spectral ID. At Living Optics, this is the information we believe we should be training machines on. With our visible near-infrared hyperspectral imaging camera, we can capture that unique description of objects that are beyond RGB and allowing you to distinguish it from other objects around it. What's more, this is done at video rate, so it can be used in the real world. And we have a friendly software stack that enables you to start augmenting your existing machine vision algorithms with this color information. Classification can be really difficult on objects that don't have shape. They're deformable or they're liquid. With the spectral information, it becomes a lot easier because you're just looking at the color of it and you're able to segment things that weren't previously possible. This is our camera. This is our development kit. We have a handheld camera that's up here. We also have the entire package included with the embedded compute, our software stack, our Python SDK, and a travel case that allows you to go out into the field, into the real world, and start collecting this data. We've tried to make it as friendly for developers as we possibly can to really lower that barrier into hyperspectral imaging. We want it out of the labs. We want it out of these factories. We want it out there in the world, people able to use it wherever they want to use it. We believe this is a step change for what machine vision can be capable of. So that's a really good marketing bit, but I really want to show you actually where we've been using our development kit in the real world and some of the unique capabilities that our camera can offer today with what we're able to solve. This will be a good showcase of how the hyperspectral imaging information complements existing machine vision algorithms. On to the main event, vineyards. So with climate change, we're seeing vineyard growers going further and further north, especially in the UK, where we're based. We have a rapidly growing wine industry there. Wine grape quality has a direct correlation with prices that can be charged for wine. So we've partnered with a local vineyard grower down the road from our headquarters. And he's a bit of a visionary. He has some really interesting, crazy ideas about getting people to adopt individual vines for their own personal wines that they want to create. And so he's looking for value on how to understand the health of his vines at a grape and leaf level, but make decisions at a vine scale. Here we have some of the spectral techniques that you can do. So on the left-hand side, we have the standard image of a leaf, RGB, standard machine vision cameras. And on the right-hand side, we start to see what some of the basic spectral techniques, such as NDVI and MCARI, can show you about the health of the vines and what's going on. We've taken a short video here. So this is our camera in action at the vineyard. We're showcasing the chlorophyll content here. It's quite a short video, so I'm just going to replay it again. It's not going to play. That's OK. This is a real-time footage. What you're seeing here with the leaves of the different color is the chlorophyll content, and that gives you an indication as to how healthy the plant is. We're collecting large data sets over this latest growing season, and we're starting to analyze those with more detailed spectral techniques, looking to correlate it with existing technologies such as BRICS metrics, which tells you the ripeness of the grape, the sugar content, and things like that. We're also starting to look at how, using the leaves, you can see the water stress, heat stress, things like that, things that we're starting to see with more and more weather extremes that are happening around the globe. Specifically on the BRICS metric, this is quite a slow and labor-intensive method for understanding the ripeness of the grape. It's also a very, very small sample size. So you get a refractometer, you pick a grape off the bit of the vine, you blend it together, and you look to see what solids and soluble sugars are present in there. With the Living Optics camera, we can provide a passive and real-time measure across your entire vineyard with up to 100% sample size. Eventually, we're hoping that these grapes get into some great wine and that we can all go and do some taste testing to really see the value of our camera. This is another slide. So on the left-hand side, we see another use of the data set. So within our camera, we have a standard RGB sensor alongside our hyperspectral data set. So you can leverage existing machine vision algorithms such as depth anything. And you can get some depth information using just the RGB sensor and really start looking at blending your existing data pipelines with this hyperspectral information. We've also got my colleague Dan here. I didn't ask his permission for this photo, so I apologize, Dan. He's living his dream, looking like a Ghostbuster here. And you can see our camera, our development kit, and he's walking up and down. This is an apple orchard here. But this is how easy it is for use for people. So, other unique capabilities that our camera is capable of. We're used to seeing results of deep learning and huge neural network machine learning techniques that have been made in recent years. It kind of shows with enough data, you can basically do anything you want, but there are still limitations. When you want to apply it to a particular problem, you generally have to augment data sets with thousands and thousands of frames and images that you want to solve for the problem that you're looking for. And this takes a long time. It takes a lot of cost. So one of the things that we believe our camera offers is that massive reduction in cost because we have that inherently more information at the outset. You don't need to provide it with as many frames. You can do it on a subset. Here is a video that's out of our HQ. We are just looking at the spectral information, and we've used a basic classifier to showcase some materials that are around. So we have our tarmac on the road, we have some artificial grass, we have some real grass, and we have some concrete slabs on the path. That video did not work. OK. All of these videos you can see at the end at the website, livingoptics.com/demo. Unfortunately, they're not working here today. Locating anomalies. So because everything has a unique spectral fingerprint, we are able to isolate those individual spectra and use our software to track them based solely on their spectral angle metrics as they go around the world. What we have in this scene is we have one of my colleagues who is a spectral tracker. He is walking along the street, and if the video plays, there we go, this one will play. What you can see here is our camera running about 30 frames per second. It's tracking him down the street using that spectra that we've isolated, and you can then reacquire as it goes away. No, it's not going to replay. That's a shame. What we can also do, based on that spectra, is that something that's quite unique is that if you get an object that hides the particular object that you're interested in, because we are on a pixel-pixel basis, you can still re-identify it as it's hidden behind and augment with segmentation-based algorithms. One of the interesting things that we're looking at is if you have multiple of our cameras, if you select and isolate a spectrum on one of them, you can hand that off to an additional camera and track a subject as it moves across a site or a system. So again, something that's quite unique with spectral information. Finally, we have another example of using our camera. On the left-hand side, we've benchmarked it against some existing YOLO models that are here. On the top axis, we have the accuracy improvements, the ability to uniquely identify an object and segment it. And on the bottom axis, we have our inference speed up, which is in orange. YOLO S is our benchmark. YOLO L, we see there's a degradation in how fast it can apply this, slight increase in accuracy with our detector methods. So here we are just adding some spectral classifiers into a YOLO segmentation model. And you see here that because it's so lightweight, we're able to speed up drastically the inference and improve the accuracy. The segmentation is a little more involved. We put it through, take that spectral classifier again, you put it through a segmentation pipeline, optimize against it with some additional data, and then put it into a segment anything. This is an example that we've taken in our pair orchard. What you see here is this is using our LO segmenter. We have the green dots refer to the spectral sampling points that you have in the world. And then where the segment anything algorithm has determined it's a good enough cluster, it's then bounded that box. This has not been optimized. If we provided it with a lot more data, we would start to expect to see some of these pairs, which have been spectrally identified in the background as they've been hidden by leaves, would also get selected. So there's a lot of optimization to do, but I think it's a really good example of what our camera holds. That was a lot of information. This can be applied to so many applications. I chose the viticulture because it's one of our largest data sets. I know it's a problem that a lot of people are interested in. So I'd like to raise a glass to those, or a metaphorical glass, sorry, to our vineyard growers around the world. And if you're interested, please come and talk to our booth more. We have a live demo showcasing some oil segmentation based on the spectra alone. And as I said, there's a few more demonstration units across different applications that you can go and visit at that website. Thank you very much. That's all I have.
Thank you, David. That was a very nice application example of hyperspectral imaging.
Thank you.
Questions from the audience?
Stunned silence. I love it.
I don't see any questions, so maybe there's one. Do you still get visitors at your booth that ask hyperspectral imaging? What is that?
Yes, I think it's still a very new technology, and there's a lot of questions and education that's needed to understand that there is all this extra information available in the world that, because we've been limiting ourselves with RGB to date, that we just haven't been aware is available to be used. So yeah, I think there's a lot of education to still be done. But there's been a lot of really, really interesting applications that are, as they've seen what we've been able to do, they've asked some really good questions and some left field things that we haven't thought of before.
So perfect, and I think application examples really help to understand what hyperspectral imaging can really do. And I wish you all the best and a lot of success.
Thank you.
In convincing more and more applications.
Thank you.
And by the way, what you just mentioned, that you still get questions, what is that? I can second that. I also hear that from our membership, that it's not yet that clear for users.
Yeah.
Among the community, yes, it's discussed, and it has been like a trend topic for years at Vision. But what is exciting is that we see more and more applications, application examples, and that is going to convince end users how strong and how powerful hyperspectral imaging is.
Definitely. I think the point at which I can easily explain it to my mother about what I do, I think that will be a really good place that we can start. So, yeah.
Perfect. Thank you. And by the way, if you dropped in late and couldn't follow all of David's presentation, it's professionally filmed. So thank you again to all the technicians here and behind this wall. It's professionally filmed. It's streamed live, and it will be available on demand starting tomorrow. So let's really promote hyperspectral imaging. Perfect. Thank you. David, another exciting application for hyperspectral imaging is coming up. My next speaker is already with me. It's Mina from IMEC.
Shall I come?
Yes, please come up. And Mina is going to talk about drone-based corrosion monitoring of metallic towers using hyperspectral data. Mina, I look forward to it.
Thank you, Anne. Hi, everybody. Thank you for being here. My name is Mina. I'm working for IMEC, and I'm responsible for the field application engineering team at IMEC, working most of the time with the spectral imaging technology. I'm honored to be here to present one of our ongoing projects together with ILIA in Belgium, which is about drone-based corrosion monitoring of metallic towers using a spectral imaging technology. Sorry, the pointer? Is it this one? Yeah. OK, thank you. So IMEC was founded in 1984. It's actually a pioneer in semiconductor technology. We have more than 5,500 people from different nationalities working for IMEC. And our core expertise, we are actually technology providers to enable you for your industry-related application to find out the best solution for your application. So most of our revenue is actually more than 70% of our revenue is coming from collaborations with industry. So you can see that we have more than 600 industrial partners that we work with. And that's actually our main goal, our roadmap to work more and more with industry. IMEC is based in Leuven, Belgium. Here is the aerial picture of our site. On the left side, you see the 200-millimeter clean room. On the right side, we have the 300-millimeter clean room, which is the world's most advanced pilot line for prototyping. On the left-hand side, on top, we have our imager labs, where Spectral Imaging Labs is located. And we are also working on integrated imaging and other imaging-related technology and development. So what is unique about our technology at IMEC is that we are actually reducing so many of the components that was in the traditional spectral imagers, such as the grating and also the prism and other related components to that. And then we can actually deposit the color filters directly on the sensor. So by that, we can actually make much smaller cameras that can be used even on a handheld device or on many other different tools that you can easily use them in the lab or in the field. So on-chip spectral imaging filters is scalable, and it can actually be miniaturized, and it's very robust. And by just doing the snapshot, for example, imaging, we can actually get video or real-time imaging that can help for many industrial or machine vision application. We have spectral cameras in different range, all the way from visible range to near-infrared and short-wave infrared, which is from 1,000 nanometer to 1,700 nanometer. So as I said earlier, we actually design and manufacture spectral filters, and we deposit them directly on the chip. For example, here you can see a color filter, a mosaic pattern that has been deposited on the sensor. And then we have a 4x4 Bayer pattern, which provides you with 16 spectral bands in the visible range. And then it can actually be used for snapshot cameras that, as I said earlier, we can actually use it for real-time imaging and sensing. So here is a video that you get different spectrum from different leaves and materials. And then you see the pattern of the spectra is very different. And based on that, we can actually have a classification map that we can see on the very bottom right corner. And if you activate the live streaming, you can see that the classification map is still following the specific material that is moving in the scene. So this is unique about our application, that we can actually do spectral analysis on real time. We have also devices or the cameras that can be used for handheld devices, or it can be used on a moving platform like a tractor in a farm or between the trees. So we can actually take care of both the movement of the platform and also the movement of the trees or the leaves, which is really robust. Our sensors also has been used on a unit that can go on a drone platform, and it's used for some agriculture applications. And also, I'm going to show you that in this application related to corrosion monitoring, we also used this specific sensor on our drone payload. But we also have provided sensors for satellites for remote sensing of the Earth and the land covers of the Earth. So in this specific project, as I said, we actually tried to monitor corrosion on the high voltage metallic towers. Why did we decide to do that? Because inspecting corrosion on high voltage tower is a very risky and time-consuming process. It usually requires people to climb the towers, which is very risky, and it's also, you have to turn off the whole power, and it's not really beneficial, and it's time-consuming. People have tried to use RGB imaging on the drone to be able to differentiate corrosion from coating, but with RGB imaging, we are limited to only first visible range and also limited bands, so the false positive was actually very high. And that's why we decided to use a spectral imaging for this matter, because you get more information from different ranges, visible, near-infrared range, and you have also more information, so you have more than 3 bands, and that can enable you to specify where the corrosion or the other surface anomalies are. We started this project by some feasibility study in the lab. So we received some samples from a real demolished tower. These samples were from different types of coating and different types of corrosion that was occurring on them. So we made a lab setup, and we scanned the samples under controlled light condition, one by one, with 2 different IMEC snap scan cameras. So with both VisNear, which has 150 bands in the visible to near infrared range, and also with a SWIR, a snap scan camera, which has more than 100 bands in the SWIR range. And we could see that actually with the results of our laboratory test that we can actually detect corrosion, and not only detect corrosion from the paint, but also sometimes we can see the difference between different types of corrosion. If it's a superficial corrosion or if it's a severe corrosion, that can also be distinguished by spectral data. Also, we did some other tests in the lab that we put some other surface anomalies that look like corrosion in the visible range to just see if we can get use of the spectral information to mask out the outliers. For example, in this case, we put a dry leaf, and also we put some soil on the samples, and you can see that the spectral behavior, in this case, in the near infrared, it's completely different from the corrosion. So that means that we can actually differentiate corrosion and the other surface anomalies on the towers. Then we went one step forward. We actually put the same samples outdoor because we wanted to see how the spectral behavior changed under ambient light and all this atmospheric condition. In this case, we used the snapshot cameras, both in near and in the SWIR. And then we analyzed the data. We also used our first drone prototype to look at the way that we can actually scan a real tower. This prototype has 2 snapshot cameras from IMEC in vis and in near spectral range with more than 30 bands. So we defined also a workflow that we start from acquiring hyperspectral data from this drone unit that we have in the vis and in near spectral range. We correct the data. For example, if it's demosaicing is required or the spectral correction is required, we do all the pre-processing. Then for the segmentation of the tower, because it's important that we can segment the 3D reconstruction of the tower, we can segment the tower from the background. Sometimes the towers are located in a farm with like vegetations as background, so we wanted to do the segmentation to only see the towers. And also it's important to go to the element base. So corrosion is happening on different parts of the tower, but for the company that we are working for, it was important to know on which element this corrosions are occurring. So we can also segment the tower based on the different elements. And at the end, we go to the classification. For the classification, we use the paint spectrum as a reference spectrum for calibration, because it's very difficult to put a white tile outside. It's not really possible, because we're also with the drone is moving. We are moving around the tower. So we decided to use the paint spectrum as the reference spectrum, and we calibrated based on that. Then afterwards, we did the outlier detection with our classifier. And at the end, we used the fully constrained least square on mixing for detecting corrosion from the paint. Also, for the accurate 3D reconstruction model of the tower, we added a LiDAR sensor to our drone payload. So this was a hardware and also software integration into our existing drone unit. And you can see that with using the LiDAR data, we can actually get a more robust 3D reconstruction from the tower based on the position of the cameras and also based on the LiDAR information. This was actually also improved by adding a lens with higher focal length. So the lenses that we were using on this drone payload was only 24 millimeter focal length, but we also use 50 millimeter focal length lenses, and then we could actually get also a very good 3D reconstruction from high resolution, higher spatial resolution, hyperspectral data. So if it's a really accurate model, we can go for the LiDAR, but if we want, let's say, average 3D reconstruction to high accuracy, then we can use the hyperspectral data by just using a better lens. So at the end, the results of this project was showing that we can actually differentiate corrosion from paint on the high voltage metallic towers. We can also get a 3D reconstruction model from the towers by using either LiDAR data or by mounting high resolution lenses on our hyperspectral data. We also add the HDR feature to our software to be able to collect data from different integration times, because it's also important for segmentation of the tower to sometimes if you have shadow or if you don't have enough light, then it's better to have multiple integration time acquisition. So that was also helping us for this 3D reconstruction segmentation of the different parts of the tower, and this was an added value for us. We also realized that the near data is a useful range for detecting the corrosion, and it's also providing the highest signal-to-noise ratio, because sometimes when you're going outdoor, the SWIR data cannot really provide the high signal-to-noise ratio. The outliers were also differentiated from the corrosion, so that was also one of the added value compared to the RGB imaging. And so far, our classification models have been validated on the lab data. We had samples both inside the lab and outdoor that we could actually get the ground truth information and validate our classification. But for the outdoor data that we have collected, we are still waiting for the ground truth. And so far, we have been scanning several towers. They didn't have really that much corrosion, but yesterday, my colleagues were actually in the site with a tower that had a lot of corrosion, and then we're hoping to be able to validate our classification software on this specific tower. So IMEC, as your technology partner, we're actually providing you with both off-the-shelf camera, but we can also go for custom design cameras or filters based on your application. So you can see that we can actually, we have a roadmap of starting from feasibility study for your specific application and see which specific wavelengths or which specific spectral ranges are more useful for your application, all the way to the proof of concept and prototyping. And we can even do some low-volume manufacturing, like up to 500 wafers per year at IMEC. And we can also, for high-volume manufacturing or production, we can transfer the knowledge and the procedure to the production labs that are bigger than IMEC, and they can provide you with high-volume production. So thank you very much for listening to this presentation. I would be happy to visit you also on our booth. And if you have any question, I'm here to answer your questions. Thank you.
Thank you, Mina. Another very interesting application.
Applications, indeed.
Of hyperspectral imaging. Questions from the audience? I don't see any.
OK.
So maybe you mentioned it, but I don't remember it. I have a question. Sure. I was informed by a drone manufacturer that it's very difficult to find a camera that's not too heavy.
Indeed. And that's,
so may I ask which camera you use?
Yeah, indeed. That's actually the advantage of IMEC cameras that are actually very small in the form factor, and they're also very light. That's why we call it miniaturized spectral camera or spectral filters. So they can actually use them easily on drones because it's actually very low light, maybe in the matter of few hundred grams. And that's not going to be a problem for any drone application-wise. Yeah.
OK. So maybe I was not attentive enough. So you produce cameras, and you then use them for applications.
OK, so maybe I should explain better that our core technology or our core expertise at IMEC is providing sensors. So we're actually depositing color filters on the sensors. The sensors can be just CMOS sensors or any other sensors that we get from the partners. And we have some off-the-shelf cameras because, of course, we want to know where we can actually use these cameras, but we're not really camera manufacturers. So we can actually even give the sensors to people who work with the laparoscope, for example, in the surgery room, and they can integrate either the small cameras that we have, or they can just put the chip inside their sensing tool, and they can integrate it into their own sensing tool. So that's actually the benefit of using IMEC sensors or IMEC spectral filters, because they're actually very, it's easy to adapt and integrate it into a new, let's say, sensing tool.
OK, so thank you for your explanation. Now
You're
I got
welcome.
it.
Thank you.
Perfect.
OK.
What's the time saying? We have another 3 minutes. We always wait because people in the live stream, they might wait and they expect to start it right on time. I can just again mention for those who just joined, all the presentations are available in the stream tomorrow on demand. And make the best out of your day at Vision. Talk to the experts, grab them at their booth and say, hey, there's something, I have an idea, I want to know. Please talk to them. So that's why trade shows are there. Thank you. My next speaker is already with me. My next speaker is Markus from OPT Machine Vision. And Markus is going to talk about advanced solutions in tap bending detection for machine vision. So, Markus, you may start.
Yeah, thank you very much. Thank you for the opportunity to showcase our solutions here. We're at OPT. We do a lot of projects in different kind of regions, and in this way we would like to introduce a bit more about our solution, what we did with our global partners and our staff in tap bending with machine vision. So short about, give you some introduction about OPT. We're a Chinese-based company in leading for vision components and a big software supplier for factory automation globally. For that, we see us as a world-class manufacturer what can be adjusted to every kind of machine vision application. This is the big brain behind. With our global network, we're doing any kind of applications with more than 2,800 employees. And like you can see, you find us everywhere in the world. So that's why we established our branches as well here in Germany with 2 subsidiaries in Stuttgart and in Berlin, but also in every kind of the world where you need our solutions. When we talk about tab bending and about machine vision, we always have to capture an image. For that, we use nowadays our own camera portfolio. This starts with 0.3 megapixel and can go up to 150 or more megapixel in the future. In this case, we don't go up to 150. We will stay in the normal ranges. We do this always from scratch for our projects to establish a hardware what is ready to use for everyone in the branch. So having an image needs also having a small lens, and this is also one thing what is always matching to our hardware is the second supply of the lens. So, but enough about OPT, now let's talk about tab building. First, what do we do? What is the thing? We have 2 methods for battery tab forming process. One process is segment cutting and winter welding. It's also mainly part of the stacking machines. So you have the positive and the negative plates, and they are cut into 2 pieces and matched together. Or you have the second plate, the continuous winding, where you also wound positive and negative parts together and execute this with a laser cutting process. Beside these processes, you have always the thing about finding the perfect cutting process for the laser, for example. Like you can see on the upper side, an OK sample should be looked like that the overlayer is folded over and the rest is there. But for any kind of processes, we don't have only the good forms. We also have the energy where we have the bench a bit too small, the tab is damaged, also the tab is ringed. This is also not working for the continuous projects. These are the basics, but there are some specifics where it's quite difficult, especially the variants and the misalignment in the machine is very complicated in this record. The tabs are very difficult because they have different shapes. You have to think we have 2 different materials with the anode and the cathode, and has to become together, which makes always a natural reflection. Then we have the reflection challenges. What I mentioned here is with significant reflection over the time, and also the difficulties that the inner labs are difficult to cut directly. What did we do here? We did this with one of our clients in China together over the long time. And we brought there, together with our internal staff, a technical solution what is based out of a hardware, software, and also the integration part, what we did here. And this is a combination of light sources and image solutions. I will go on the next slide a bit more in detail, because then it's more clear. We separate images from aluminum and copper. We don't want to mix match this together for better image quality, and also to define in which kind of directions we want to go. Due to the fact that in any kind of the tab welding processes, there's not much space for any kind of machine vision products, we had to use here a lot of prism to proceed any kind of light sources. And for the last but not least, we introduced in this project our first deep learning project, where we're working direct with partners, but this is also our one. So, but what did we do? You have to see the tab is laying in the middle. On the left side, you have the anode, and on the right side, you have the cathode. And every side is inspected with 3 cameras. I will go in detail about which cameras we are using here, but you have a light source for every camera, from the upper, from the lower, and from the left side. So in the end, every tab will be inspected by 6 cameras, and every step. The hardware is just normal monochrome matrix cameras. From the upper side, and from the other side, we have colored cameras. For the forefront side, we have 20 megapixel cameras with a field of view of 60 to 40 millimeters, so it's not so big, to get a pixel resolution from 0.01 millimeters per pixel from the side. And from the end, we get also, with a 20 megapixel sensor, a 100 to 73 millimeters image for a pixel resolution of 0.02 millimeters per. All in all, this is only the camera hardware. In this project, we preceded 6 cameras, of course, 6 lenses, but also very unique lights. For this application, we designed a new light solution based on a half-shaped ring light, what illuminates exactly that what should be seen. So the tab from the over on the lower side, and like we saw in this case, there's not much space. So like we thought, we're using Prism, we're using any kind of solutions that is possible to see the tabs in this case, because there's no space. And how does it look like in real? From the upper and then the lower side, like I said, from one side we're using matrix cameras in monochrome, and from the other side we're using the color camera. We have the tabs, what needs to be inspected. So this is just the ground truth for fulfilling up the pipeline for deep learning. To conclude this, we have the left side, the right side, and the end phases, which are now separated for our pipeline, what comes next. The tabs are now laying side by side. We can detect the foldings, and we can also detect the surface. But now we had the issue, how could we proceed? Because normal standard algorithmic is quite hard to implement for these, where you have very different sources of raw material, what always look a bit different. Okay, from the images like we saw here, we're reducing the reflection, but you can't never reduce reflection to 0%. So what did we do here? We worked here with our own Deep Vision 3 platform. This is an AI vision platform, what is a self-development core platform. We have some features there inside. Okay, we're using a supervised algorithm, this is clear, but we have an automatically assigned computing power to reschedule the task, especially when you get a new charge for tabs. Because every charge of tabs we found out are a bit different, and there's always a need for adjusting the AI model behind. Due to the soft nature of the tabs and the very high number of the tabs who are laying side by side, we have a very high variance. We have also the reflection, and this brought us to the point that we needed a very big comprehensive model in this case. We had also the issue, we had not so many good or for example, bad parts to implement. So far we had to train algorithmic on synthetic data where we produced on our own. Our OPT solution was that we, like I said, we produced the data with a generated advertising network to target the deep learning aspect behind. Then we started with the ground data. We have the anomaly detection in the base with 3 classes. We had the winding, what would be good. We have the reflections, what would be okay, and we have the NG. So, for example, a winding is allocated now on the right-hand side on the lower point, where you see, okay, there is it. And due to the fact of the model that it is trained, it is workable. But then we have also something different applications. So, for example, this is also the side effect of the depth, where you see in the red box, for example, an NG of, okay, here's something different. And we have to see that there's not only these accurate image, there are any kind of barriers here in this defect. We can see also on the lower side it's defect, but on the upper side, okay, this should be clear. But this is one example. Then we made the first dry run in our office, and where we tested 50 OK and 50 NG before we made the deployment. For the first results, it was great. We convinced the client to proceed with us. Then we made the first deployment in the machine, where it was looking like that we saw the same what we had some minutes before. We had the upper and the lower side on the management board. But then we had some difficulties, and this is something what faced us a long time till we could finish it because of the software parameter. And this is the misanalytics, what we always see, and where we see our strength with our own employees who can transform this for the future. Because on the left side you have this misanalysis, in the middle, then also the second one in the middle, and also the correct detection, what was misclassified. And this brought us to this point that due to the fact the customer also said, okay, now we want to improve ourselves a bit more, and went into the next direction. So far, we had to find now these errors. Then we had a retraining, and now what was working. These images were quite easy to find because the tabs are in this shape that it was easily to calculate. But this brought us to one point, what we learned in this application, that the anode was quite different to annotate than the cathode, because of the material, and also because of the reflection, and because also of the cutting process before. The cathode is softer than the anode, and this brings to more frequent tab stacking, and also to a recognition anomalies what we have behind. That's why we had to train 2 different models in the end for each side. And also, the different foil material causes to inconsistent and in the detection of the defects. But in all, we started the deployment. We retrained our model over the time, and then after the total results of 80,000 images, we could find new missed defects after retraining and retraining the model. But the only thing what was to mention, and also what the customer wants to improve in the future, is the overkill images, what we saw some minutes before, because here with an overkill rate of 0.8, this is something where we believe we can improve for the future. But that's it, how we fulfill a project. Thank you.
Thank you, Markus, from OPT, Machine Vision. Questions from the audience? Maybe you? No. Okay, so no question. Markus, it seems you covered it all. I would like to say thank you to all my 3 speakers. It was really an exciting session, beyond the visible. So I'm always amazed what is possible with hyperspectral imaging. Great, so have a nice day at the Vision, all of you. And yeah, we will be back soon for the next session on machine vision, software, and AI.